And so the question is, how do you build those agents? Well, we now have a great system. I'm so happy to announce this for you. This is called our DGX Lepton. DGX Lepton, what you're looking at here, is a whole bunch of different clouds. Here's the Lambda cloud, the AWS cloud, your own developer's machine, your own system. It could be a DGX station, Nebius, Yoda, N-Scale. It could be AWS, it could be GCP. NVIDIA's architecture is everywhere. And so you could decide where you would like to run your models. You deploy it using one super cloud, so it's a cloud of clouds. Once you get it to work, once you get this NIMS deployed into Lepton, it will go and be hosted and run on the various clouds that you decide. One model architecture, one deployment, and you can run it everywhere. If you want to deploy it in the cloud, you got GB200s in the cloud. You're going to deploy it all the way on your DGX Spark or DGX station, no problem. And so Lepton will help you do all of that. Let's talk about industrial AI. We're working on industrial AI with one company after another. This is BMW building their next generation factory in Omniverse. And this is Toyota building a digital twin of their warehouse in Omniverse. And when you build these warehouses and these factories in Omniverse, then you could simulate its effectiveness before you go and physically lift and move things around to discover it wasn't optimal. And so the ability to do everything digitally in a digital twin is incredible. But the question is, why does the digital twin has to look photoreal? And why does it have to obey the laws of physics? The reason for that is because we wanted ultimately to be a digital twin where a robot can learn how to operate as a robot. And robots rely on photons for their perception system. And those photons are generated through Omniverse. And robots needs to interact with the physical world so that it could know whether it's doing the right things and learn how to do it properly. And so these digital twins have to look real and behave realistically. Okay, so that's the reason why Omniverse was built. As you know, everything that moves will be robotics. Everything that moves will be AI-driven. And the car is the most obvious next one. NVIDIA builds the AI supercomputers to train the model. The AI supercomputer for Omniverse digital twins. We also build the AI supercomputers for the robots itself. In every single case, whether it's in the cloud, for Omniverse, or in the car, we offer the entire stack. The computer itself, the operating system that runs on top of this computer, which is different in every single case. This computer, high speed, sensor rich, must be functional safe. In no circumstance could it fail completely. And so the safety requirement's incredibly high. And now we have an incredible model that sits on top of it. This model that sits on top of it is a transformer model. It's a reasoning model. And it takes sensor in, you tell it what you want it to do, and it will drive you there. Takes pixels in, and it generates path plans output. So it's a generative AI model based on transformers. Incredible technology. NVIDIA's AI team, AV team, is incredible. This is the only team that I know that has won end-to-end self-driving car challenge at CVPR 2 years in a row. And so they're the winner again this year. 1 billion cars on the road, 10,000 miles a year on average, 10 trillion miles. The future of autonomous driving is obviously gigantic. And it's going to be powered by AI. At the core of everything we do here with AV is safety. And we're really, really proud of our Halo system. It starts with the architecture of the chip, and then the chip design, and the systems design, the operating system, the AI models, the methodology of developing the software, the way we test it, everything from the way we train the models, the data we provide for the models, all the way to the way we evaluate the models. NVIDIA's Halo system and our AV safety team and capabilities are absolutely world-renowned. We've been at this now for coming up on 10 years. And so this capability is world-renowned. I'm really proud of it. The same thing that's happening for cars is happening for a new industry. As I mentioned earlier, if you can generate video from prompts, if AI can perceive, it can reason, and it can generate videos and words and images, and just now with cars, the path, the steering wheel path, why can't it also generate locomotion abilities and articulation abilities? So that fundamental ability for AI to revolutionize one of the hardest robotics problems is around the corner. Humanoid robots are going to be a thing. Now, why hasn't it happened? Well, the reason for that is simple. Today's robots are too hard to program. Only the largest companies can afford to install a robot, get it to teach it, program it to do exactly the right things, keep it sufficiently surrounded so that it's safe. That's the reason why the world's largest car companies all have robots. Almost everybody who's a Mittelstand or small, medium companies or mom and pop restaurants or stores or warehouses, it's impossible to have that programming capability until now. We're going to give you essentially robots where you could teach them. They'll learn from you. Just as we were talking about agentic AI, we now have humanoid AI that can learn from your teaching using toolkits that are very consistent with the NEMO toolkits I spoke about. NVIDIA here as well is built in 3-layer stack. We build the computer, the Thor computer. Dev kit looks a little bit like this. This is a robotic computer, completely self-contained. Dev kit sits on your desk. These are all the sensors. And inside is a little supercomputer Thor chip. Just really, really incredible. And these, yep. I could imagine getting one of these inserted like that. Now, the big challenge of humanoid robotics is the amount of data necessary to train it is very, very hard to get. And so the question is, how do you do that?